Hello and welcome. This video is part 1 of our 5-part basic skills mathematics review series, and given that very little can get done in mathematics without understanding real numbers, that's where we're going to start our review. Notice that if we measure the distances between objects or the time between events, these different kinds of measurements can be taking place. All kinds of distances or time periods are possible, right? We do not just get nice whole numbers like 2 units, 3 units, etc. We also get fractional distances like 2 3/4 units, or decimal distances like 6.5 units, or even irrational distances like pi units, which would be the exact distance around the circle of radius 1/2 unit. Which is also called the circumference of that circle. In mathematics, we have a home where all these numbers corresponding to real measurements, which are called real numbers, live. And that place is the real number line. The real number line consists of all those positive numbers, a number indicating no movement or no measurement, which we call 0, and the opposites of those positive numbers, which we call negative numbers, as you I'm sure know by now. To create a number line, we must first decide what measurement unit we're going to use, and then we can include any measurement we like. We could use the metric, which is also known as the international system of units, or we can use the standard or the British system of units. The metric is familiar mostly to people in the rest of the world, as opposed to here in America, because in America we are still using the British system, so we're all familiar with inches, feet, yards, or miles, etc. And this is just for measuring distance. Of course, we have measurements for volume, etc. in the metrics in the British system, and as well as in the metric system. So the metric system is a very simple system because it's based on the powers of 10. So there's a nice relationship between all these units, which we will see as we proceed. So here's a sample of a real number line. Notice that somewhere toward the middle we usually put a 0, and middle is a very arbitrary word here. There is really no middle of the real number line, right? Because it moves infinitely in both directions. So theoretically speaking, there is no real middle to it. But of course, since we always draw a finite segment to look at, even though we put arrows indicating we're dealing with a line, but this nevertheless right here is a finite segment, so we usually mean the middle of that segment is when we say the middle. We don't actually mean the middle of the number line, the real number line. All right, so of course here we can see that 1 unit is about that much. Now that could be, any kind of unit. This looks to be around an inch, right? So then we just make marks every inch and move forward, right? And of course we can have partial units. So of course, instead of going 1 whole unit, I go 1/2 unit to the right of 0, I end up with positive 1/2. I go 1/2 unit to the left of 0, I end up with negative 1/2. So all the positive numbers live to the right of 0, and all their opposites live to the left of 0. 0 itself is neutral. It's neither positive nor negative. And here, of course, notice we have a mirror image of what's going on here, except with negative numbers. So if we have 2 3/4 here, you can be sure that there's going to be a opposite of that number on this side, and which is also called the additive inverse. And for pi, we have negative pi, etc. Very simple, very powerful, infinitely interesting, because The more you study this, the more amazing it gets. One quick fact, just to pique your interest, is the fact that if you pick any two real numbers, let's say 0 and 1, okay, it's very easy to show that there are actually infinitely many numbers between those two real numbers. Now, we picked 0 and 1, right? I could use also 0 and say 0.01. It doesn't matter how close the numbers are. The amazing thing is you can still fit infinitely many numbers between them. Here's a quick proof of how you can have infinitely numbers between 0 and 1, right? You can pick the number halfway between them right there, and then you can pick the number halfway between 0 and that number, that'll be a quarter. Pick the number halfway between 0 and a quarter, that'll be 1/8, and then between 0 and 1/8, that's 1/16. Notice this process does not have to stop, and so you get all these numbers starting with, so you get 1/2, and then you get 1/4, 1/8, 1/16, and on and on and on. And notice that all those numbers are going to be somewhere between 0 and 1, right? So we just showed very quickly that there are infinitely many numbers between 0 and 1. Now, there is nothing to stop us from doing that for any two real numbers, right? So we can pick any two real numbers. So just call this x and y, right? Then find the number halfway between them. You know, of course, that'll be x plus y over 2. And then start the process, right? Find the number halfway again. And in this way, you can show that there are infinitely many real numbers between any two real numbers, no matter how close they may be. And in this kind of way, you can see that the set of real numbers is a real magical wonderland. Most of modern mathematics is described through the notion of what we call a set. A set is, of course, any collection of well-defined objects. The key word here is well-defined. So you have to be able to clearly state what the members of a set look like. So you can't just pick any collection of objects and say, oh, here's a set. No, you have to have some way to define them. Then you have yourself a mathematical set. Now, the set of real numbers, missing an S here, of course, no matter how closely you check these things, you always leave something out. But imagine there's an S there. Here, we'll put one here. The set of real numbers, which we notate using this kind of different looking R with the double bars, right? Basically, it's the set of all the numbers on the number line, which we just learned about. So we take all the numbers that are on this line together and put them inside a set. Then you have yourself the set of real numbers. So remember that when we say a set of real numbers, we're referring to the set containing all those numbers, not just the simple ones like 1, 2, 3, etc., -1, -2, -3. No, all the ones, the decimals, the fractions, all of them, the rational ones, the irrational ones, all of them comprise the set of real numbers. Now we say that a set A is a subset of another set B if all the elements of set A are also contained in set B. Symbolically, we write if X in A implies that X is also in B, then A is a subset of B, denoted by this notation. It's kind of a sideway U with an equal kind of sign on the bottom. Now, this just means A is a subset of B, but it doesn't get rid of the possibility that A and B may be equal, right? That's why it says it's a subset, or it may be the same set, okay? So if as long as we use this notation, then we can't say that A is what we call a proper subset of B. So if one set is a subset of another and they happen not to be equal, then we say that the first set is a proper subset of the second set, and we write A is a subset of B, and we no longer put this equal bar beneath, right? So remember, without that, that's a proper subset, and with that, it leaves the possibility of the two sets being equal. As you can see in this image, we have a set A, which is fully contained inside another set B, and the two sets are not equal. So here we can say A is a proper subset of B. And of course, even if the two sets are equal, you can say that A is a subset of B with the equal sign underneath, and a subset relationship still exists. It's just not a proper subset relationship. And we distinguish that using a different symbol when a proper subset relationship exists, where notice that any point inside A is also inside B, therefore A is a subset of B, and there are points inside B that are not in A, therefore the two are not equal, and A is indeed a proper subset. While we are on the topic of sets, before we move on to look at the proper subsets of the set of real numbers, or R, I thought it would be nice for us to understand the distinction between two words that play a very significant role in mathematics, and that is the difference between and or. And in these tables, which are called truth tables, we can see the difference between these two words as being quite dramatic, because if you're dealing with two statements, P and Q, and you want to know the status of the truth or falsehood of the or statement resulting from those two statements, then notice that as long as one of the two statements is true, here both are true, in here P is true but Q is false, and here P is false but Q is true. As long as one of them is true, the statement P or Q is going to be true. The only time an or statement becomes false is when both the original statements are false. For example, suppose the statement P says today is Saturday, and the statement Q says today is Sunday. Well, as long as the day that you're considering happens to be either Saturday or Sunday, the statement P or Q is going to be true, because you're saying today is either Saturday or Sunday, and it would be true. However, if you make that statement on a Wednesday, then notice both of those statements would be false, because today is not Saturday and today is not Sunday, so the or statement would be false as well. Now, when it comes to and statements in mathematics, and this is all basically coming originally from the field of logic, but we apply it in mathematics all the time as well. Mathematics in many ways can be thought of as applied logic. Notice that it's a very different story. P and Q, the and statement standard of truth is very tough. In order for an and statement to be true, both statements have to be true. That's the only time an and statement becomes true. As long as either one is false, then the and statement is going to become false, right? Looking at the same two statements, there's no way today can be Saturday and today can be Sunday, right? So so even if today is one of those days, then you would still have a true false scenario because it wouldn't be the other day and it would be false, right? So in order to get a true statement here, we would need statements both of which are possible, right? For example, if we were to say today is Saturday and it is a day, and today is a day in the month of April, for instance. If that happens to be a Saturday in April, then the and statement would become true. You could say today is Saturday and today is a day in the month of April. Then the statement would become true, the and statement. Or statements in logic and mathematics are called disjunctions, and statements are called conjunctions. Again, we're not going to be applying this right away in this video much further, but we will revisit these concepts as we proceed in our study of algebra. It's just that since we did an introduction to sets, it's very good to understand some of these concepts that are very related, and as we'll see in a minute. Now that we've learned about sets, we can go ahead and talk about the two most important operations we can perform on sets. And one is to take the intersection of two sets, and we can represent that using beautiful diagrams called Venn diagrams. And basically, when you look at the intersection of two sets like A and B, U here is a universal set that contains both A and B. So it's kind of providing context for us. And when we say A and write this upside down U symbol and then B, the way you read that is you say A intersect B equals basically any member of the universal set which is in A and in B. Remember, in order for and to become true, that means it has to be in both of them, and the only way that can happen is if it's in this intersection right here. Okay, so the shaded area here is representing precisely the intersection of the two sets, or A intersect B. For the union of two sets A and B in some universal set, what you do is you take all the elements in the universal set which are in A or B. Remember? So when you see or in this context in mathematics, this is what we call an inclusive or. So that means it can be here or in both. This becomes darker because remember there's an overlap here. So any members in here are going to be counted twice unless you take one kind of count out, which we always make sure we do in various contexts where this kind of notion comes up. So this is the union of the two sets A and B right here, and an element in the universal set is in the union as long as it's in one of those two sets, right? And of course it can also belong to the intersection. It's very important to understand that when you see or in mathematics, you're dealing with an inclusive or. It's different from the way we use or in regular English. For example, if I say this afternoon I'm going to see a movie or I'm going to the theater, I don't mean that I'm going to do this or that or both. I mean I'm going to do this or that, but not both, right? But in this context, in mathematics, when we say or, we mean this or that or both. Now we want to go ahead and look at the proper subsets of the set of real numbers. In other words, we want to look at subsets of the set of real numbers that are different from the set itself, right? Proper subsets. All right, the simplest set we could consider when it comes to the set of real numbers is the set of numbers we can count on our fingers, right? 1, 2, 3, 4, 5, etc. We call them, you know, for obvious reasons, counting numbers, but more formally we call them the set of natural numbers. And we use this double bar notation again with n, and it's basically the set containing, you know, the numbers 1, 2, 3, etc. All right, this ellipsis at the end indicates that this pattern continues indefinitely. All right. Now notice that we did not include 0 in this set because obviously we can't count 0 on our fingers. So however, that doesn't mean 0 is not important. 0 is extremely important as a number, and there are many occasions where we may want to include 0 with the rest of these positive natural numbers. So out of that need and out of respect for 0, we create a new set, and we call it the set of whole numbers, which does include 0. So the only difference between the set of natural numbers and the set of whole numbers is one element, and that's 0. Remember, the members of a set are called elements or members. Either way, either word is adequate for that usage. All right, so to basically bring all the simple numbers on the number line together, we go ahead and throw in all the opposites of these positive numbers and include 0 as well, and we create a new set called the set of integers. So this, you know, the language, the verbiage that we use here is a little bit different. We don't say the set of integer numbers like, you know, we say the set of real numbers, natural numbers, whole numbers. Here we just say the set of integers. So this word integers kind of contains numbers in it, right? And we use the symbol z, which I believe is from German Zahlen, which means number. And there it is. Basically, it's the set containing all the simple numbers on, you know, the real number line. They're all whole numbers and their opposites together with 0, right? And of course, remember, 0 is its own opposite. So all right, so there's a compact way of writing that, which is kind of nice because it makes it look more like the set of whole numbers. But here we use this compact notation, plus or minus 1. So 0 plus or minus 1 plus or minus 2 plus or minus 3, etc. Now, sometimes in more advanced study, we look at this set of two sets, which are subsets of proper subsets of z, and we call them z plus and z minus. Z plus should look familiar to you, right? That's exactly the same as the set of natural numbers. Z minus is just the set of all the negative or the opposites of the natural numbers. And again, remember, we never say the set of integer numbers, right? Numbers is implied in the name integers. Okay, that brings to an end all the simple numbers, right, that we may encounter on the number line. And now we're ready to go ahead and look at numbers dealing with parts of wholes, right? And basically, we're going to first look at, again, the simplest kinds of fractions that are possible, because not all fractions are created equal, because you may look at 1 over 2 and square root of 2 over 2, and they're really different in the sense that this number is made up of basically two integers. This one is not. Square root of 2 is not an integer, and it never will be. So because of that, we need to be very precise about what we mean by a rational number and what we mean by an irrational number. Here it turns out that 1/2 is a rational number, but square root of 2 over 2 is irrational. So let's see what that actually means. intuitively speaking, the set of rational numbers contains the simplest types of fractions and of course their decimal equivalents. That is, fractions whose numerators and denominators are integers. But if we want to put it formally, we say the set of rational numbers equals Q, which I believe has to do with quotient, basically equals all numbers of the form m over n, right? That just means all fractions such that m and n, meaning the numerator and denominator, belong to the set of integers. And of course, with fractions, we always have to have a restriction, right? We don't want the denominator to be 0 because otherwise the fraction becomes undefined, even if the numerator is also 0. So the restriction we have is that n should not be 0. You always want to be aware of that restriction when you're dealing with fractions. Now, as it turns out, the decimal equivalents of these rational fractions are also very well behaved. And when we say well behaved, it's in this sense: a decimal equivalent of one of these quotients of integers is either going to terminate, which means it's just going to stop after a few decimal values after the decimal points, such as 2.53, stop, right? Or they repeat. So like 5.231, 231, 231, right? That's called a repeating decimal. So in short, a real number is a rational number only if it can be written as either a fraction whose numerator and non-zero denominator are integers, or a decimal number which is either terminating or repeating. That pretty much covers it as far as rational numbers are concerned. So we want to see here if any of these numbers are rational numbers. 7/3, right? Obviously, anytime I do an example for you, what I would like you to do is to pause the video, answer all the questions on your own, and then come and compare your answers. That's how you learn mathematics, by doing it. Remember, yeah, you don't watch a mathematics video like a movie. You watch it in a very participatory manner, right? As the old saying goes, mathematics is not a spectator sport, right? So you have to really be engaged. So have pen and paper with you always when you watch any video lecture, and make sure that you try the questions on your own before you watch the rest of the video. So I hope that you've tried all these and you have come back. So we'll come back now. 7/3. Notice that the numerator is an integer, so is the denominator, and the denominator is not 0. So yes, this one is a rational number. Determine if each of the following numbers is rational or not. So this one, we're going to say yes. All right, for this next one, when we look at it, it may not immediately look like in the form of one integer over another, but we know that we can put it in that form. Remember, a number doesn't need to be initially in that form, in one of those forms, either a quotient of integers or a repeating or terminating decimal, but as long as we can put it in one of those four forms, then it's rational. So here we notice that if I just carry the negative, and we know that in order to turn this improper fraction into, a mixed number into an improper fraction, we multiply 4 by 3 and add to 1. So that's going to be 13 over 4. And of course, remember, I can always write that with the negative 13 on the top and the 4 on the bottom, or I could even write it with the 13 on the top and negative 4 on the bottom. In either of those two scenarios, we have integer over integer, right? So it is a rational number. 5, right? That's interesting. You go, oh no, that's an integer, or that's an integer, or you can say it's a whole number, or you could say it's a natural number. All of those would be true statements, right? But more importantly, I can also take 5 and I can write it as 5 over 1, which is integer over integer, therefore it's a rational number. Which I'm sure you're thinking, oh wait, I can do that with any integer, right? You're exactly right. Every integer is also a rational number, but it doesn't work the other way around, right? In other words, x belonging to z implies that x also belongs to q, right? But the other way it doesn't work. Just because x belongs to q does not imply that x belongs to z. In other words, there are some rational numbers such as 7/3 that are not integers. So it's not a biconditional. We don't put a double arrow here, right? We only put a one-way arrow, right? This implies that, but this does not imply this one, right? So therefore, we can say that every integer is also a rational number. Now this one, remember, square root of 2 is not rational, and we'll talk about that in a minute. Just take my word for it for the time being. And this one is, so, but that's not good enough. We need to have both of those as integers. Mainly what I meant to say a minute ago is that square root of 2 is not an integer, not a rational number. Even though what I said is true, it's not a rational number. What we care about right now is that it's not an integer. So therefore, and there's no way we're going to be able to write it as an integer. So there's no way this is going to be a quotient of integers. So therefore, this is the first one that is not. So no, this is not a rational number. Pi is probably the most famous number that is not rational, right? So this definitely goes in the no category. And 0.1234, what do we think of this? Well, this is a terminating decimal, right? It just goes 4 places and it stops. So this is obviously going to be a yes. Now, so what that means is you should be able to take this and write it as a quotient of 2 integers, which of course you know you can do very easily. That'll just be 1, 2, 3, 4 over a 1 and then 4 zeros, right? So yes, we can do that easily. All right, how about this next one? 0.122333444. We see some kind of a pattern, right? There's you know, you start with a 1 1 and then 2 2s and then 3 3s and then 4 4s. I can tell you what the next one will be. It'll be 5 5s, right? Probably, but you have to be extremely careful. While that's a cute pattern, that's not the kind of pattern we're talking about when it comes to rational numbers. For a rational number, we need a repeating pattern, and this is not, while it's some kind of a nice pattern, it's not a repeating pattern. So this actually would be a nice example of an irrational number. So this is not a rational number. All right, so how about this one? Well, if you're familiar with square roots, you know that the number that you have to square to get 225 is what is meant by the square root of 225. So when you see this expression, you're looking for some number that you have to square to get 225. Now, if you recall, if you take 15 and square it, you'll get 225 in fact. So be very careful. Just because you see a radical, don't automatically assume that you have an irrational number. So because remember, square root of 225 equals 15, so therefore yes, it's definitely a rational number, because we can of course write it as 15 over 1, right? Just as we did up here with 5. 0, of course, yeah, why not, right? We can always write 0 as 0 over 1. So yes, that's definitely rational. How about the square root of negative 4? What number do you square to get negative 4? Well, some of you may be thinking, oh, negative 2, right? Well, not quite, because when you take negative 2 and square it, you actually get positive 4. And that goes with 2 as well, right? So if it's not one of those two, probably not going to be any real number, right? And that's precisely right, because there is no real number that's you're going to be able to square to get negative 4. So this is not even a real number. So remember, to be rational, you have to at least be real, right? So here, we don't even go there. It's a moot point, right? Because to be rational, you first have to be real, and this is not even real, so therefore it's certainly not rational. So the short answer would be no. All right, we are finally ready to define the set of those elusive irrational numbers. It may seem like a strange definition to you because it won't actually tell you what they are. It will tell you what they are not. Okay? An irrational number is basically a real number that is not rational. Now, we can get away with this because what a rational number is quite well defined, right? We have been very specific about what kind of numbers are rational. So we can just use a negation technique to define irrational numbers. So we say the set of irrational numbers P, and I think that's just to set it apart from Q. That's the reason for that, the notation, is all the numbers, all elements of the set of real numbers that are not elements of. Remember this little symbol here, it looks like a E, something between an E and a C, right? Well, it's neither. It's Greek epsilon, and it stands for belongs to, or is an element of. So it's all X belonging to R as long as X does not belong to Q, right? So basically all real numbers that are not rational. Now, practically speaking, an irrational number can neither be written as a quotient of two integers, nor can it be written as a decimal number that is either repeating or terminating. The easiest way to generate as many irrational numbers as you desire is to remember one important fact, which we will state, but whose proof lies beyond the scope of this course. But we will accept that as fact. And the fact is that the square root of any non-perfect square is irrational. So you can now, with armed with this fact that the square root of any non-perfect square is irrational, you can generate as many irrational numbers as you want. All you have to do is just take the square root of the ones that you know are not perfect squares. Like, for example, we know 2 is not a perfect square, so square root of 2 is irrational. Same with 3, so the square root of 3 is irrational. 5 is not a perfect square, on and on and on, right? Notice we've skipped 9 because the square root of 9 would be rational because it's just 3, right? Perhaps the most famous irrational number, as we said, is pi. And pi itself actually provides a real easy way to come up with as many irrational numbers as you would like as well. Just take all the integral multiples of pi. That means all the integer multiples, right? So pi, 2 pi, 3 pi, 4 pi, or negative pi, negative 2 pi, negative 3 pi. These all would be irrational numbers as well. But do note that the square roots of perfect squares, like square root of 4 or the square root of 9/25, they would be rational, because as you know, those can be simplified to integer over integer form. This one is just 2/1 or 2. This one is 3/5, right? So they are definitely rational. Now, we hinted at this earlier, but given that any integer can be written as itself over 1, all integers are also rational numbers. So we get this nested set relationship. We say the set of natural numbers, which we know is a proper subset of the set of whole numbers. We know that the set of whole numbers is itself a proper subset of the set of integers. That is in turn, now we have seen with this explanation that it is a proper subset of the set of rational numbers, which is of course itself a proper subset of the set of real numbers. So now the numbers rational or irrational, no matter what they look like, they will live on the number line, so they're both real. So this relationship holds. So then we have this other chain, short chain, right? The set of irrational numbers is contained in the set of real numbers, right? So the set of irrational numbers doesn't play nice with the rest of them, so therefore it's not part of this long nest of sets, right? But if we draw the scenario, we'll find that the set of irrational numbers here has been depicted to take such a bigger chunk of this overall set, which is representing the set of real numbers. It's just a visualization, you understand, as opposed to all these other sets that are kind of lumped together in a very small part of this large oval, which represents the set of real numbers. So why is that? Well, that's because even though both of these parts of the set of real numbers are infinite, right, meaning they have infinitely many elements, this infinity associated with the set of irrational numbers is actually of a higher level than the infinity associated with the set of rational numbers. So therefore we can safely say that there are more irrational numbers than there are rational numbers. And I state that here. The fact of the matter is, while we may like it to be otherwise, there are far more irrational numbers than there are rational numbers, much as is the case with human beings, as we know. All right, that kind of nicely summarizes the relationship between all these proper subsets of R and R itself. So do make sure you understand those, please, before we proceed. All right, another important concept when it comes to the set of real numbers is the concept of inequality. Suppose that I show you a graphic like this, right? I'm not telling you any information about the actual, number associated with that point, or that point. I'll just tell you their names. I'm calling this point A, this point B, this point C, right? But I can tell you for sure, these are actually names for these numbers, right? But what we can tell for sure is that B is greater than what? An A, and C is greater than B, right? But of course, because B is greater than A as well, C is also going to be greater than A. And the easiest way to say that is that a real number B is larger than any number A on its left and smaller than any number C on its right. So all these relationships hold, right? We can say, for example, we can say A does not equal to B, and this is just one of them. We could also say A does not equal to C. We can say B does not equal to C. We can say A is less than or equal to B, right? You may say, wait, what do you mean by or equal to? Well, remember, one of them has to be true for the whole thing to be true. And because A is indeed less than B, we can say A is less than or equal to B. And we can also say this tougher sentence. We can say A is strictly less than B. These, without the equal sign, they're called strict inequalities. So this one and this one on the bottom, both of those are called strict inequalities. So notice that instead of saying A is less than or equal to B, I could have said B is greater than or equal to A. See? And instead of saying A is less than B, I could have said B is greater than A. These are equivalent statements when it comes to this scenario. All right, so we want to determine if each of these statements is true or false, right? -7 is greater than -8. Okay, with these, when it comes to negative numbers and inequality, you have to be careful, all right? Because if you do a quick sketch, which is what I recommend that you do so that you get them right every time, you'll realize that while 7 and 8 may have this kind of a relationship on the right side, they actually have this kind of a relationship on the opposite side. So in other words, we notice that while 7 is indeed less than 8, -7 is to the right of -8. So it's actually greater than -8. So this means the statement made here, even though at first it may have looked a little bit strange, is actually true. Okay? How about this relationship? 6/7 is greater than or equal to 10/11. Well, you do not want to make any kind of a judgment about two fractions unless they have the same denominator. So that's what we're going to do first. We're going to go ahead and rewrite those with the same denominator. So we know that the common denominator here is just going to be 77. So I'm going to write both denominators as 77. So of course, to make 77, we have to multiply it by 11. So like so. Don't forget to do the same to the 6. Anytime you do something to the denominator of a fraction, you have to do the exact same to the numerator. And for the 11, we have to multiply it by 7. So we do the same on the top, right? So now what do we have? We have 6 times 11, which is 66. Now remember, this fraction and this fraction are exactly the same as far as value is concerned, right? They look different, but their fundamental nature is the same. And we want to know if that's greater than or equal to, now this is going to be what? 7 times 10, that's 70, right? What do you think? Well, now that they have the same denominator, they're very comparable. All I have to do is look at the numerators now, right? Because the denominators are the same. And I noticed that, no, this is actually going to be less than that. So as a statement, this will be false. Now this one is actually a very quick one. Remember, any number is greater than all numbers to its left, right? Now, if you look at 0 and -1000, where is -1000? Without getting really bogged down by details of the graphic, I know it's going to be somewhere on the left, right? Depending on the scale that I use. So this actually is a true statement. And you would have answered it as quickly no matter what negative number was written here. Even if it were negative 0.0000 with 10,000 zeros and then 1, right? It would have still been true. All right. Now these two decimals, they look real close, right? So how do we tell in a situation like this when two decimals are so close? Well, we'll line them up. Here's what you do. Let's go ahead and write this first number on the top. So we have 0.145679, and we put the other one below, but making sure we line up the decimals, right? So we have 1456879. All right, so starting in the highest position on the left, we start working our way, right? And as long as these are the same, we keep going, right? So notice here, those are the same, check. The next one's check, check, check. This is the first spot where there's a discrepancy. They're not the same, right? So that's exactly when you stop, and whichever number has the larger digit at that location, which is this one, this is going to be the larger one, and this is going to be the smaller one. So look at what we're saying. We're saying the smaller one, right, is less than or equal to the larger one, right? So is that true? Of course. So this one actually was a true statement. So that's how you determine with these kinds of decimals that look quite similar. All right, so next we want to look at what's called the additive inverse of a real number. This is also known as the opposite of the real number. This was the older terminology. This is the more modern terminology. All right, so for any real number x, the additive inverse of x, also known as the opposite of x, is obtained by multiplying x by -1. In other words, the additive inverse of x is -1 times x, which of course is just -x. So we want to find the additive inverse of each of these numbers that are shown here. So of course for 7, the additive inverse will simply be, so the inverse will be -1 times 7, which is -7. How about for -7? Well, remember, this is going to be a mutual relationship. If one number is the inverse of the additive inverse of another, then that other is also the additive inverse of the first number. So I equals the opposite of -7, which is basically 7. All right, so that's just -1. There's an invisible 1 which I didn't write, but you could always write. For -pi, same business. We don't treat it any differently. We take -1 and multiply it by it, and of course that becomes positive pi. For 0, -1 times 0 is just going to be 0. So as you know, 0 is going to be its own additive inverse. So now we can finally discuss what we mean by the absolute value of a number. We define absolute value in two ways, algebraically and geometrically. It actually turns out that the geometric definition is much more intuitive and will be a lot more helpful to us as we proceed in this class. But in more advanced classes, you'll encounter this algebraic definition more often, and it's really important to know it. But we are going to be utilizing this definition, the geometric version, more often in this class. So the algebraic definition of absolute value says for any real number x, the absolute value of x, denoted by of course, x with 2 bars around it is defined as, well, it's x itself is, if x happens to be non-negative, you have to be very careful here. You don't want to read that as positive, because if you do, you miss 0. So out of respect for 0, again, we have a different name for this kind of a entity. When x is greater than or equal to 0, the English translation of that would be that x is non-negative. That's one word. I'll write it down. And no space or dash or anything like that needed, okay? So here, instead of saying this, we could write if x is non-negative. So that would be in words, right? And it's the opposite of x if x actually happens to be negative. Now this time here we can say negative, right? Because it's not less than or equal to 0. If it were, we would have said non-positive, right? But here it says strictly less than 0. So if you were to translate that, that would be if x is negative. All right, so I don't know how this m found its way here. Let's just go ahead and get rid of it. Some kind of a typo. All right, so let's go ahead and look at what the absolute value of -5 would be using this algebraic definition of this function. Actually, it turns out to be a function as well. That's a name we'll understand much better later on. And notice it's got a two-part kind of description, this function. Again, this kind of a scenario you'll encounter from time to time. We call them piecewise functions, and it's very good to get exposed to them early on in your mathematical work. All right, so absolute value of -5. So let's see. Remember, this is a conditional. If it's something, if it's a certain thing, you have to go up here. If it's a certain other thing, you have to go down here. Now, -5, where does it fit in? Is it less than 0 or is it greater than or equal to 0? Of course, it's less than 0, so the absolute value of -5 is going to be the opposite of -5, which is actually going to be 5. Now, the geometric definition of absolute value is much simpler. It just says, look, for all x belonging to R, the absolute value of x, again denoted by the same, double bars against x, is going to be defined as, not actually double bars, just bars around x. You got to be careful with, what we say. All right, so we say absolute value of x is just the distance between x and 0. Beautiful, simple, intuitive. Okay, so now let's look at the absolute value of -5 using that definition. Well, let's say this is 0. Let's say 1, 2, 3, 4, 5. We have 5 on this side. -1, -2, -3, -4, -5. Of course, I didn't need to draw these, but I drew them for a reason, because I want you to see how it takes the same number of units to go from 0 to 5. There's 1, 2, 3, 4, 5 units. That's the distance between 0 and 5. Remember, that's what distance is. How many units separate two numbers, right? And notice that the same number of units separate 0 and -5. So while this distance here is 5, so is that distance. So that's why absolute value of -5 is 5, which is the same as the absolute value of 5, because both 5 and -5 have the same distance from 0, namely 5. Alright, so we're gonna get some more practice with these, and then that's gonna wrap up this video for us. Alright, so when you want to evaluate expressions like this, you have to be very careful and deal with the absolute value internally first, and then continue with the rest of the operations. So here I'm to actually evaluate the absolute value. You never multiply into an absolute value or a sign or anything like that. So just deal with the absolute value first. We know the absolute value of -7 is just the distance between -7 and 0, so it's just 7. So we just go ahead and say that's 3 minus 7. Now we know that's just going to be -4. In one of our videos in this 5 video series, I will go over all these in much more details, but we'll just kind of wing it this time, right? So the absolute value of 3 minus 7, remember, always do the operation first inside and then take the absolute value. Don't split that up as the absolute value of 3 minus the absolute value of 7 or anything like that, because it's not true. So that's going to be the absolute value of -4. That's just 3 minus 7. Now we apply the absolute value, and that's just going to be giving us 4. Now in here, remember, we're going to work our way from the inside out. That's how you deal with nested groups of parentheses, right? Work your way from the inside out. So notice that's just going to be -3 minus 7. So we have negative of -3 minus 7, because the absolute value of 3 is just 3. So that becomes negative of -10. And that is going to be, now we're ready to take care of this operation. So that's just negative, and inside there we get 10, and that's just going to be -10, like that. Okay, so very simple, just have to be careful. Alright, so here we'll go ahead and take care of the absolute value of -4/5, which is 4/5, and multiply it by -1, so we end up with -4/5. How about the absolute value of 0? Well, that's going to be, by definition, the distance between 0 and 0 itself, right? Because the absolute value of any number, including 0, is going to be the distance between that number and 0. So what is the distance between 0 and 0? Of course, 0. One quick application of the absolute value is providing us with a really nice way of finding the distance between two numbers on the number line, which we call the one-dimensional distance formula. Now, we already know that we can find the distance between two numbers like b and a here if we just take the larger one and subtract the smaller one from it. So we go a minus b, and that will give us the distance. For example, if we have say let's draw a number line. Okay, so if we are dealing with, for instance, 3 and 7, so just to make this come to life, you know that we can take the larger number 7, subtract from it the smaller number, and we get the distance. So this distance here is basically 4 units, right? Now, it would be nice in situations where we don't know exactly what the value of the numbers are if we can not worry about which one is smaller and which one is larger. And the absolute value actually lets us do that without any concerns, because notice that if we take the absolute value of 3 minus 7, which is one of the problems we did in the previous screen, we end up with the absolute value of -4, which of course is 4, because it's the distance between -4 and 0, which is 4 units. But if you take the absolute value of 7 minus 3, which is, you know, this one reversed in the order, you also end up with absolute value of +4, which again gives us 4. So in order to get this distance of 4, it didn't matter whether we did absolute value of 3 minus 7 or 7 minus 3. Both of them will end up giving us the distance. So that's exactly what the distance formula tells us. This, of course, is the one-dimensional distance formula. Once we study the Cartesian coordinate plane and we get 2 dimensions that we deal with, then we'll come up with a different distance formula using the Pythagorean theorem. But for now, notice that the distance between any 2 points can be found by taking the absolute value of the difference between those 2 points. Now, those 2 numbers, of course. Now, it doesn't matter whether A is the larger one or B is the larger one, such as on the case on the left. The absolute value of A minus B or B minus A will both give us that distance. So that is one really nice quick application of the absolute value. This, of course, should not be at all surprising, because A minus B and B minus A are always opposites of one another. And of course, we know that opposites have the same absolute value. So 5 and -5 have the same absolute value, namely 5. 10 and -10 have the same absolute value, namely 10. Pi and -pi have the same absolute value, namely pi. So here is the quick proof of that fact. Notice that we can take A minus B, we can write it as -b plus A using the commutative property of addition, and then we can factor out a negative basically using the distributive property in reverse, and what we'll be left with is B minus A. So notice that A minus B is the opposite of B minus A. You can show in exactly the same way, and you should do this on your own before you come back and look, but you can do the same kind of business and show that B minus A is the opposite of A minus B. So that is why the order of the subtraction does not matter within the absolute value, because then you'll be taking the absolute value of 2 opposites, which of course is always the same. So to find the distance of 2 points on the number line, or 2 numbers on the number line, just basically take the absolute value of their difference in any order that you like, and you'll find the distance. Do notice that this, of course, works if one or both of the numbers happen to be negative as well. Like the distance between -5 and 7, we can either do 7 minus -5, or we can do -5 minus 7, and in both cases we'll end up with 12. And that's how you find the distance between 2 numbers on the number line, without, of course, worrying about which one is larger and which one is smaller. If you do know which one is larger and which one is smaller, of course, you can always take the larger and subtract from it the smaller, as always. All right, that brings us to our last problem for today. We just want to determine whether each of these statements is true or false. Do try it on your own, then come back to the video, please. All right, so here we're going to take care of the absolute value first. What's the absolute value of -7? That's 7. So we want to know if 7 is greater than 6. Well, is it? Of course it is. So therefore this one is true. How about absolute value of -7 is greater than 7? Well, that's going to be saying that 7 is greater than 7. Remember, no number is greater than itself. So therefore, this is going to be false. Now, be very careful not to quickly jump to the conclusion that this one is false as well. Because remember, this means 7 is greater than or equal to 7. Remember, that translates into 7 is greater than 7 or 7 is equal to 7, right? That's what greater than or equal to means. Now, I know this is false, but I know this is true. And if you remember your truth tables for or, what happens here? As long as one of the statements is true, the or statement is going to be true. So therefore, this one is true. All right, so this gets a little bit more abstract because it's not telling us what x is. It's just saying, hey, no matter what x is, its absolute value is going to be greater than or equal to 0. Well, if you think about it, no matter which one of the definitions you use, the absolute value of a number is always going to be non-negative, right? So therefore, this is telling us something that is definitely true. Try it with different numbers to convince yourself, okay? How about this one? It's saying the opposite of the absolute value is less than 0. Well, you got to be a little bit careful here, okay? Because it's very tempting to say, yeah, that's true. We just said this is true, so this should be true too, right? For very similar reasoning. Now, the only question is that going to be true for all real numbers? Well, these two aren't exactly the same, are they? This one says greater than or equal to, this one says less than. So because of the fact that the equal to is missing, this is going to end up being false because it won't work for 0. Note when x is zero, we get negative absolute value of 0 is less than 0, which is negative 0 is less than 0, which is 0 is less than 0, which is of course false. Okay, and remember, when you say a mathematical statement is true, you mean it's always true. But when you say it's false, it doesn't have to mean that it's always false. It means there is at least one place where it fails, and that is what we call a counterexample. Now, notice, for example, this would be true for x equals 1, because you get negative 1 is less than 0. It would be true for x equals 2, 3. In fact, it's true for any real number other than what? Other than 0. Try it. Plug in any number other than 0, and this is going to be a true statement. This is how tough we are in mathematics on the standards of truth, and that is why other disciplines can rely on mathematics. It's because mathematics is so hard on itself. Okay? All right, and that basically does it for our first basic skills review video, and we covered real numbers and their proper subsets. I hope you've learned much, and I will see you at the next video, where we're going to cover decimals and percents. Be safe until then.